Welcome to the deep dive. Today, we're jumping into something we all use every single day, but maybe don't think about much. I mean, until it, zaps us. We're talking electricity.
Yeah, that invisible force.
Exactly. And our mission today, we're taking your sources, and we're really going to unpack the absolute fundamentals, starting right at the beginning, assuming you're just taking your first steps.
Mm-hmm. Back to basics.
Totally. So think about those moments, Maybe it's winter, you pull off a sweater, snap, or your hair goes wild after you brush it.
Static cling, yeah.
Right. You felt those little jolts, that weird clinginess. Okay, so let's break this down. How does that even happen? Those little sparks, that thing, what is it?
Well, what's so fascinating here, I think, is how something that feels really complex, powering everything.
Yeah, our whole world.
Right. How it can actually be understood if you look at the tiniest parts.
Yeah.
The building blocks. If we break those down, the bigger picture of electricity, from that tiny spark you mentioned to the whole power grid, it starts to make sense.
Okay, so if we want to get electricity, we need to start with, everything. What's stuff made of?
Mm-hmm.
If you could just keep dividing something smaller and smaller and smaller, eventually you get to these incredibly tiny things called atoms.
The fundamental unit, basically.
Right, the smallest bit of an element that's still, that element. But here's the kicker. Even though they're ridiculously small, atoms themselves can be broken down further into even tinier bits.
That's right. Yeah, the atom isn't the end of the line. It's actually made of even smaller pieces.
Yeah.
You've got protons, neutrons, and electrons.
Okay.
And the protons and neutrons are kind of clumped together right in the center. That's the nucleus.
The core.
The core, exactly.
Right.
Now, trying to picture atoms, that's really tricky. They're just unbelievably small. So small that actually how we think they look, our models, have changed over time.
Ah.
You might have heard of Bohr's model. He pictured electrons sort of orbiting the nucleus like planets around a sun.
Right, I remember that from school.
Yeah, it's a common image. Now, we understand it's more like a cloud. The electron's position is more about probability.
Right.
But honestly, forgetting the basic idea today, for this deep dive, thinking of electrons moving around the nucleus, that works. It gives you a good starting point.
Okay, got it. So this is where it connects back to those everyday zaps, right? That static shock.
Exactly.
Pulling off the sweater, combing your hair, that snap, that's electricity actually being made somehow. So how does that happen with these atoms and electrons? What's going on there?
It all boils down to something called electrification. So normally an atom is neutral, balanced. It has the same number of positive protons inside the nucleus as negative electrons flying around it.
Equal numbers, okay?
Yeah, let's say 4 protons, 4 electrons.
Yeah.
It's stable. But what if that atom grabs an extra electron from somewhere else?
Ah.
Suddenly it's got more negative bits than positive bits.
Right.
It'd be 5 electrons, but still only 4 protons. Now that atom is negatively charged.
Makes sense. More
Cool.
negative stuff.
And the opposite can happen too. If it loses an electron, kicks one out.
Then it's short on electrons.
Exactly. Now, it has fewer negative electrons than positive protons. Maybe 3 electrons, 4 protons. So the atom becomes positively charged.
Gotcha.
And that whole process, gaining or losing electrons, changing from neutral to charged, positive or negative, that's electrification. That's how you get these little bits of electricity started.
And this happens through friction, like rubbing things.
Right. Your sources mentioned frictional electrification.
Yeah.
That's the balloon on the hair example. Or even peeling electrification, like when you peel plastic wrap off something. Just separating materials can cause electrons to jump.
Okay, so these atoms are now charged. They've gained or lost electrons. They've got this new electrical property. So we need a name for this, right? Like if you get really good at something, you get a title. Like a black belt or, a grandmaster. So what do we call matter that's become electrically charged?
We just call it electric charge. Simple as that.
Electric charge. Okay.
And yeah, it comes in 2 flavors, basically. If something's positively electrified, we say it has positive charge. If it's negatively electrified, it's got negative charge.
Test and negative charge. Easy enough.
But here's something important. The amount of charge on just one single electron, it's tiny. Like incredibly, incredibly tiny.
Hey.
Think about water. A single H2O molecule isn't really a drop of water, right? You need tons and tons of them together.
Billions, probably.
Exactly. It's the same idea with charge. 1 electron's charge is almost nothing in practical terms. So we needed a bigger unit. It actually takes a huge number, about 6.24 times 10 to the power of 18.
Whoa, okay, that's a lot.
It's a mind-boggling number, 6.24 quintillion electrons. That many electron charges grouped together is what we call 1 coulomb. That's our practical drop of electric charge.
1 coulomb. Wow, that really puts it in perspective. So, okay, we've got this electric charge. Does it always, like, move, or can it just sit there? Like, sometimes you just want to stay on the couch.
Yeah, that's a great analogy, actually. That's basically static electricity. Static means not moving, right?
Right, stationary.
So static electricity is charge that's kind of collided on a surface and prefers to stay put. It's not flowing anywhere.
Yeah.
And yeah, most of us just think of it as annoying, those shocks, the clingy clothes.
Definitely. Just a nuisance.
But, and this is pretty cool, that static electricity, it's actually incredibly useful in a lot of technology. Way more than just shocks.
Really? Like what?
Well, think about copiers or laser printers. They actually use static electricity in a really clever way. They create a charged pattern on a drum. The toner particles stick to that charged pattern, and then it gets transferred to the paper.
Huh. I never thought about that.
Right. And those fine dust masks, many of them use electrostatic filters. They're treated with static charge to grab tiny little particles out of the air.
Wow.
And even simpler things. Plastic wrap clinging to a bowl, that's static. Dust cloths that seem to magically attract dust. Static again. They even use it for painting cars to get a really smooth, even coat.
That's actually amazing. So static isn't just annoying zaps.
Not at all. It's doing a lot of work behind the scenes.
Okay, so that's the electricity that likes to stay put, the static kind. But what about the electricity that does move? The stuff that powers things?
Exactly. So the opposite of static, or stationary electricity, is electricity that's in motion. We sometimes call this dynamic electricity. Dynamic means moving. Active.
Dynamic.
And this moving electricity flowing usually through wires, metals, conductors. That's what we commonly call electric current.
Ah, electric current. That sounds familiar.
And that's the key. Static is charge sitting still. Current is charge moving. And that moving current is what we harness to do all sorts of things.
So let's sort of recap. We went from the tiniest things, atoms.
Protons, neutrons, electrons.
Right, those bits inside. Saw how just moving an electron around, gaining or losing one, creates this thing called electric charge. Positive or negative.
Yep, electrification.
And then we figured out that this charge can either sit still, that's static electricity, which is surprisingly useful.
Copiers, filters.
Or it can move, and that moving charge is electric current.
That's the core idea.
So just by following that path, you've basically got a handle on the absolute foundation of this thing, electricity, that you use every single second, pretty much. It's a good shortcut to understanding it better.
It does raise an interesting thought, doesn't it? Now that you know it's all about these tiny particles shifting around, creating charge, and then maybe flowing as current, how does that change how you think about, say, flipping a light switch? Or plugging in your phone charger?
Yeah.
Next time you get that little static shock or you see your phone charging up, maybe picture those electrons. Billions upon billions of them, either jumping suddenly or flowing steadily. Does that spark any new questions for you? What else do you wonder about now?